Hi, my name is Ahmed Hosein. Our team was tasked to build a glass pulverizer to be retailed or wholesaled. The skills I bring are the abilities to do research and the use of Microsoft Office software. The parts of this project I was tasked to do are the background research and the literature and patent reviews.
My name is Raechard Bernard. The skills I brought to my team are my abilities to innovate and conceptualize, as well as my experience in utilizing CAD software such as SolidWorks and AutoCAD. For this project, I was tasked to develop the three conceptual designs.
My name is Dharshan Sookoo. The skills I bring are creativity and critical thinking. I was tasked with the client and user requirement, key attributes, and metrics.
My name is Jarret Churaman. I am skilled at solving mathematical problems and facilitating communication among the team members. I was tasked with the functional analysis section of the project.
We begin with the introduction. A brief background on the history of glass bottles is as follows. Historically, glass manufacturing was a tedious process that lasted several days. Only when the glass blowing technique was invented did the manufacturing process simplify. Technology has since advanced to the glass furnace and beyond, allowing for large-scale production and improved efficiencies. However, this abundance of glass products resulted in significant amounts of wastage, although glass is recyclable. Our problem statement states that there is a need to reduce the volume of waste that eventually ends up discarded in landfills. Glass must be disposed of in such a way that it is able to be reused or recycled easily. Our aim for this project is to design a machine that pulverizes glass bottles into glass cullets. The project objectives are to conduct a literature review and patent review to realize the aim, to incorporate user and client requirements into the design specifications, to formulate the design to meet the specifications and to select the best design, to test the chosen design via simulations, and finally to build a prototype model focusing on either form or function. Before beginning the process of designing the device, relevant literature was studied. It was found that the landfills in Trinidad and Tobago are approaching capacity and waste volume must be reduced. Glass can be recycled in many ways since it does not lose its mechanical properties when reused. For instance, glass residue can be used in place of river sand to improve the properties of cement mortar. However, all glasses cannot be used for all purposes. Colorants added during the manufacturing process cannot be removed, and also, glass types determine the cullets they produce. Now, 4 patents were reviewed in order to familiarize ourselves with related devices that are already in use. In the first patent, titled Bottle Crusher, glass bottles are fed in the intake slot one at a time. The bottle rolls down the incline and through rubber flaps. It then falls under the influence of gravity onto rotating hammers, which break the bottles into large fragments. These hit the insides of the chamber to break down further, eventually falling into the collection bin. The second patent, titled Bottle Crusher, is a manual device. The lid can be opened via a hinge and a bottle can be placed on the lower jaw cradle. The upper jaw is attached to the lid, and so closing this lid will cause that jaw to impact the bottle. The many tooth members allow for a reduction of force needed to break the bottle. If the bottle is too small, the rod connected to the upper jaw can be driven downwards. In either case, cullets fall through the spacings in the lower jaw into the bin. Patent 3, titled the Glass Grinding Machine, bottles are fed in and allowed to slide down a ramp. They then hit vertically rotating impact blades, and the ensuing glass shards impact the chamber and lower grate at high velocity. When the grains are small enough, they slip through the grate into the lower bin. The final patent, entitled Glass Crusher, glass is fed in from above. The rotating hammers break the bottles, and the glass pieces hit the corrugated inner chamber. The outer rotating discs bound the work area, preventing the glass shards from flying out of the machine. The number of hammers and central discs can be varied depending on the required cullet size.
client and user requirements. After enough research, a list of the client's requirements were generated. If I am able to meet the client requirement, the design should have a low price range, a moderate range of production, an average quality of material, a lifespan of 5 years with little or no maintenance. It should be safe such that no PPE or specialized training is required, and it should be able to pulverize the glass into smooth pieces that can be held. User requirements. The machine should be able to be used with a low level of skills. It should be able to be placed on the counters or in corners. It should be able to process one bottle at a time as fast as it can be fed into the machine. And it should be robust enough to require limited downtime. Design specification. The machine can process glass bottles. It must fit under counters of restaurants and bars. It must use the standard 110-volt power supply. Must have the proper shielding or guards. Cullets must be easily collected. Vibrations from the machine must be minimized. Standard components must be used. It must have a built-in fail-safe, and it must be simple to use. Key attributes. Based on the design, the key attributes were developed, and these are user-friendliness, cost, stability, safety, and noise. The metrics. The metrics use a scale of 1 to 3 in this project, with 1 being the worst case scenario and 3 being the best case scenario. We now move on to pairwise comparison, where the relative weighting of each design indicates the importance of each key attributes. In the order of most important to least important, we can see that user-friendliness is the most important, followed by safety, then by cost, then stability, and lastly, noise.
Here we have the functional analysis. The first step in the functional analysis is the black box. It consists of an input, a process, and an output. The inputs on the left are glass bottles, electrical energy, a signal to start the crushing process, and sometimes setting the bottle size. In the middle we have the process, which is pulverizing glass, and on the right we have the outputs, which are glass cullets, waste, dirt, and energy lost as heat, sound, and vibrations. Moving along, we have the transparent box, which is similar to the black box, however it shows all the sub-functions involved in pulverizing the glass, as well as the inputs for each sub-function. Then we have the means tree, which shows the main function as well as the sub-functions and the means by which they may be achieved. The morphological chart is how we explore possible ways of implementing the different sub-functions. It also aids in developing a conceptual design.
Moving on to conceptual designs. Using the morphological chart as mentioned previously, 3 conceptual designs were developed. Conceptual Design A. The figure to the right shows a partially transparent isometric view of Design A without its body casing. The design is 24 by 10.5 by 34 inches, which makes it compact and easy to store. Glass bottles must be manually loaded into the machine's crushing chamber via its top opening. The rotating arm and drive lever force the mobile toothed plate against the stationary toothed plate, which pulverizes the glass bottles. This is the device's pulverizing mechanism, which is powered by a motor and belt drive system. After pulverization, the cullets fall through the exit space at the base of the chamber into the collection bin. A door at the base of the device allows for easy placement and removal of the cullet bin. The body casing is easily removable for maintenance purposes. Conceptual Design B. The figure to the right shows an isometric assembly of the design's internal components. Also being a compact design, this concept measures 24 inches in both length and width and 44.5 inches in height. Glass bottles must be manually loaded into the machine's chimney, which leads to the crushing chamber. Driven by a motor and belt drive system, a rotating disc drives the hammer up and down, which impacts and compresses the glass bottles within the crushing chamber. This is the device's pulverizing mechanism. Sharp teeth at the base of the crushing chamber, as well as at the base of the hammer, aids in the pulverizing process. Under the vibration of the crushing chamber, the cullets fall through the mesh holes at the base of the chamber into the collection or cullet bin. Similar to concept a door at the base of the device allows for easy placement and removal of the collection bin. The easily removable body case allows for easy access to the device's internal mechanical and electrical components for maintenance purposes. Conceptual Design C. The figure to the right shows a partially transparent isometric view of the design's internal components. This is the largest design compared to the two previously mentioned, measuring in at 24 by 28 by 54 inches in length, width, and height, respectively. Bottles must be manually loaded into the chimney, which leads to the pulverizing chamber. A rack and partially tilted pinion retracts the pulverizing plate upwards while simultaneously compressing 4 springs. When the pinion loses contact, the rack slips and the pulverizing plate is forced downwards by the springs into the glass bottles, pulverizing them in the process. The toothed crushing chamber base aids in the pulverizing process. The cullets fall through the small mesh holes at the base of the chamber into the collection bin, which may be easily moved through the doors. Similar to the other two conceptual designs, the body is removable for maintenance purposes. Rated matrix. Each design concept was evaluated using the metrics shown in the previous slides to obtain the raw score for each key attribute. Using this design selection matrix and the rated matrix, the weighted scores were then calculated. It was found that design B had the highest total weighted score, and hence it was the selected design for this project. Description of final design. The main components of the final design includes a hammer system, a crushing chamber, a crank wheel system, a chimney system, a motor and belt drive system, and a body casing. The hammer system. This system consists of a rigid connecting rod and a hammer. The connecting rod links the hammer to the crank wheel, which transfers motion. The hammer spans the internal cross-section of the crushing chamber and has a series of teeth at its base, which increases the pulverizing effect upon impacting the glass bottles. The chamber entry cover plate blocks the bottles from entering the chamber when the hammer is at its lowest point of its stroke. Crushing chamber. This consists of a hollow cuboid known as a crushing chamber, which has a toothed and meshed base to aid in the pulverizing and removal of the cullets from the device. The supporting legs act as both a shock absorber and a support. The removable backplate allows easy access to the chamber for cleaning and maintenance. Crank wheel system. This system consists of a solid disc with a cantilever extended face, a ball bearing, a shaft, support stand, pulley 1. The bearing allows for rotation of the shaft, which is connected to the disc and pulley 1. The support stands holds this assembly together. The cantilever on the face of the crank wheel serves as a point of connection for the hammer system. Chimney system. This system consists of a cylindrical tube, a support stand, clamps, and a separation plate. The cylindrical tube provides a smooth path for the bottle to reach to the crushing chamber. The clamp and supporting stand provide rigidity to the chimney. The separation plate serves to both provide a base for the supporting stand and to partition the mechanical and electrical components from the user. For user safety, a leather flap was placed over the chimney opening to protect the operator from glass cullets that may travel back up the chimney. Body casing. This consists of a front case, a back cover plate, a door, and a base plate. The removable front case and back cover plate surrounds the internal components, providing a protective barrier between the operator and the machine. The door allows for easy access to the cullet bin. The base plate is the foundation of the device upon which all other components are built, and it is hence very important to overall device stability. We have come to the end of this presentation. My design team and I would like to thank you for your time and attention.